All right, we're here. I want to save that one. There we go. All right, so I got rid of the old. All right, let's talk about friction. All right, Sir Mix-a-Lot. Let's get our friction on here. Okay, now here's how it works. It basically here on Earth and for Physics 210, here's how friction works. Now, friction is interesting. Friction is an interesting thing. All right, if I look at the forces here, now we're not going to do these types of forces, but we are going to look at static and kinetic frictional force. I think this is an interesting slide here. Look, when an object is in contact with a surface, there's a force acting on that object. The component of this force that is parallel to the surface, okay, so if I want to pull this along, is called the frictional force. And friction has these little microscopic contact points, even if it's an incredibly smooth surface. So it's microscopic. So this could be as like a speed skater skate on ice, and it's still, there's still some friction there. Well, actually, their ice is a different story because it gets a film of water on top of it up to negative 40 degrees Celsius, which is the same thing as 40 Fahrenheit, negative 40 Fahrenheit. Water always has a film on it, so it makes it really, really slick. But if we polish this down, polish this down, we'd still have these little microscopic points of friction where things rub against each other. You all know about friction, okay? But the thing is, so it makes no difference about the contact surface area because the points of where it contacts is relatively small. I mean, it's dinky, all right? So the surface area, the size of the surface area does not matter when we're calculating the coefficient of friction. There's two kinds of friction. I'm not going to go through their slides. I'm just going to tell you. There's static friction. This is why we can walk, and this is why our tires push us down the road. Static friction, not moving. Because if you think about it, when you're walking, is your foot, if you watch someone in slow motion, is their foot that's pushing off, is it moving? No. So static, not moving friction. Okay? And then there's kinetic. And all kinds of different surfaces have different frictions, okay? And here's the other term, coefficient of static friction and coefficient of kinetic friction, moving. All right? These depend on what the substance is. Like say for snow with a fiberglass ski, the coefficient of kinetic friction, which we'd call mu of K. I will show you the slide there. Okay. Here it is. Mu of S for static friction, mu of K for kinetic friction. And it depends on the material. It depends completely on the material, is equal to, mu of K is just given. Or we might have to calculate it depending on what else we have. But the kinetic frictional force of something is equal to mu of K times the normal force. Okay? And then mu of S, and then mu of S, which will be given because each substance has its own static coefficient of static friction. It's just a coefficient, so that mu of S. And so the force of static friction is equal to mu of S times F of N times the normal force. All right, so let's go ahead and look at these slides here. They might do a good job of explaining this. All right, so when two surfaces are not sliding across one, the friction is called static friction. If it's not sliding, there's no movement, no movement. I'm pulling with a smaller force, pulling with a larger force, and then finally I'm almost to the breaking point where it's going to go, and so I got a huge force. So right there at the maximum, the static frictional force is less than or equal to the maximum static frictional force. And the maximum static frictional force, F of the maximum, to finally get it to move, the force that's needed to finally get it to move is equal to mu of S times F of N. So if you've got a block on an incline like this, that equals 0. Oh, sorry. If you got an incline on a block like on an incline like this, because they're not going to in contact anymore, it's falling. All right. But the max, you pull harder and harder and harder, and it's mu of S times the frictional force. Now, what did we just see in the previous problem with an incline? All right, with an incline, we saw this. Here we are, we've got an incline. Ooh, this is a big one. Let's say this is 50 degrees. Okay, that's stupid. Let's do it this way. Here we go. Let's say we got an incline of about 25 degrees. Frictionless, of course. Got a mass up here. M1. Now we've already seen it's got an mg going this way and a normal force at the angle. We did the rotation and we found that some of the forces in the y direction are equal to 0. Which is equal to the normal force, minus, and when we rotate this down, or we rotate it 25 degrees and make it level, I've got F of N, mg going like this. Then I've got mg cosine theta and mg sine theta. All right. So, frictionless force, or we've actually got friction. Now, since we have friction, guess what? It goes this way. So let's put a static frictional force here. Static means, since I've got an Fs, what does that mean? That means the acceleration of the object is 0. It's stuck. It's just sitting there. It's stuck. Okay? So we look at the sum of the forces in the y direction is mg. Oh, and then we've got this static frictional force going this way, parallel to the thing. So what does F of S equal? Well, some of the forces in the y direction are equal to Fn minus mg cosine theta. Okay, so mg cosine theta is equal to the normal force. All right. Now, some of the forces in the y direction, or in the x direction, are equal to 0 too, because it's not moving. It's static friction. All right. So I've got the only force I have is F of S. Plus mg sine theta. That force is there, but it's not accelerating. So therefore, the static frictional force is equal to mg sine of theta. Okay? There you go. Okay, now let's say that something is accelerating. Now let's say that the block is actually moving. Draw it again. Horrible block, I'm kind of hurrying here. So now it's accelerating in this direction. It's accelerating. Ah, now I've got a kinetic frictional force going this way. Okay. And I've got mg sine theta going this way. Just remember this. When a block is on an incline, the force that it's going down, the gravitational force in the x direction is equal to mg sine theta. The normal force is equal to mg cosine theta. Okay? Is equal to the normal force. All right? So now, sum of the forces in the y direction is equal to 0. This is m1, which is equal to f of n minus mg cosine of theta. So therefore, the normal force is equal to mg cosine theta. And therefore, the kinetic frictional force is equal to mu of k, the coefficient of friction, times the normal force, which is equal to mu of k mg cosine theta. New equation. Then to calculate the acceleration, some of the forces going in the x direction are equal to mass times, except it's going down that. We let that be. Is equal to minus f of k plus mg sine theta. That's how you'd calculate the acceleration. We've got max is equal to minus mu of k mg cosine theta plus mg sine theta. All right. And we can calculate mu of k. We can calculate mu of k because it's moving, and we'll say, what if it was going at a constant velocity? Well, then this would equal 0. Mu of k would equal mg cosine theta. And if we solve for it, we'd wind up with the sine over the cosine, which is equal to tangent theta. For when it's not accelerating. All right, we'll talk about all that stuff next time in class. Done here.